next, let's look at how we can apply what we learned just now to some of the steady flow engineering device. Open system specifically, okay, where there's a mass exchange. Okay, and we'll be looking at a few examples: nozzle, diffuser, turbine, and compressor. Okay, but there are more examples such as heat exchanger and pump, but we won't go into every single one of them, mainly because of the time constraint as well. So we'll look at the general concept, and then you should able to apply to the rest of them. Okay, so just remember, all these devices, all these systems, we analyze it under steady flow. So which means the change of mass in the control volume over time is always zero. Okay, so in a way, there's no mass accumulation in this kind of system when we analyze them. Okay. So first of all, nozzle and diffuser. Okay. Nozzle, we've seen the example before. Okay. So it changed the velocity. Across this device, this control volume, okay, the property will change. Specifically, nozzle increase the velocity. So when velocity increase, pressure will drops. Okay, so sometime when engineer need to speed up the flow, we'll use a nozzle. We change the area. Of course, area will be different as well. This is A1. This is A2. So area will be different as well. So by changing the area, we can manipulate the velocity, you can manipulate the pressure. Diffuser is the opposite. We slow down the velocity so that the pressure can build up. Okay, of course the area will be different as well. So it's really just two opposite devices. Nozzle to increase the velocity, diffuser to increase the pressure. Okay. And one thing for sure about nozzle and diffuser, work is zero because there's no work transfer in the process. Nozzle and diffuser doesn't do work at all. Okay. But there might be heat exchange in the process. There might be, depending on whether it's an adiabatic nozzle, adiabatic diffuser or not. Okay. If it is fully insulated, if the question says it's fully insulated or it's adiabatic, then this can be zero. Okay, it depends on whether it's insulated or not. Okay, when there is no heat transfer, then the equation really reduced to this only. It's only the energy exchange throughout nozzle and diffuser is really just because of the mass itself. If it's an adiabatic nozzle and diffuser. Okay. One thing for sure, doesn't matter it's adiabatic or not, work transfer always equal to zero. Okay, so this one thing that you should know about nozzle and diffuser. It changed the property, but then it doesn't involve in any work at all. Okay, potential energy, most of the time elevation doesn't change. The nozzle is not moving as well, so potential energy, kinetic energy of the system is always zero. Okay, this here, this is for the system. This here, the small cap one, they are referring to the flow. So the change in the flow kinetic energy, there is, but then change in the potential energy in the flow is 0 as well. Okay. So quickly, let's look at one example. So this is a diffuser in the aircraft engine. Okay, so diffuser and nozzle is quite commonly used. In fact, not commonly used. It's in fact being used in the aircraft engine, the same aircraft that everyone takes when we go travel. Okay, so it says that air at 10 degrees Celsius and 80 kilopascal enter a diffuser of a jet with a steadily with a velocity of 200 meter per second. Okay, inlet area. So it's a diffuser. So I should just draw like this. Okay, 10 degrees Celsius, 80 kilopascal. Velocity is 200 meter per second. The flow go in. Okay. Inlet area 0.4 meter square. I should write this properly. V1. Straight V. Okay. And then A1. The air leaves the diffuser with a velocity that is very small compared to the inlet velocity. Okay. So going out here, V2 is almost 0. That's what the question say. Okay, so determine the mass flow rate of the air and the temperature of the air leaving the diffuser. Okay, so the mass flow rate is basically we can analyze from the inlet because the inlet has most of the property that we need. It's rho 1, A1, V1. Okay, V1 we know, A1 we know. Rho is basically P1 over RT because this is air. It's an ideal gas. So therefore we can apply ideal gas equation for it. Okay, so that's how we can find out the mass flow rate at the inlet of the diffuser. Okay, and this is our control boundary, by the way. Okay. Then how can we find out the temperature leaving the diffuser? This is a steady flow device, so therefore M2 got to be equal to M1. Okay. And then we have to write the energy equation, which looks like this. Okay. And here, there is no heat transfer involved, not being mentioned. For diffuser, definitely the work transfer is 0 as well. So therefore, we come to this equation here. Okay, so H1, we can calculate based on CP T1. Okay, and H2, obviously, we can calculate based on CP T2, which T2 we don't know it, T1 we know. Velocity 1 we know. Velocity 2, the question say is very small, almost 0. So we can treat it as 0. Okay, so we rearrange it, the whole thing. Here, the mass got cancelled out. Okay, even if you don't get cancelled out, you know the number. So we can just plug it in, but you can be cancelled out anyway. Okay, so then eventually, you will get to the T2, which is about this temperature. Okay, so that's how we can solve a problem for diffuser. If it's nozzle, pretty much the same way as well. Okay, so you can see the pattern is always you find out the state at one side first, and then you relate the second state using the energy balance equation most of the time. That's how we solve a open system. Okay, even the closed system, pretty much the same method as well. Okay, that's how we solve thermodynamics problem in general. We find out the one state first, because from state 1 to state 2, in between, this is the process. Okay. Here is an example of nozzle. Okay. So here is a steam. Okay. So steam means that we have to find the property using steam table, thermodynamic table. We cannot apply ideal gas equation here anymore. Okay. So here as well, steam at this temperature. Okay. Sorry, this pressure, this temperature, steadily enter a nozzle whose inlet area is this much. So now this is a nozzle. So I'll draw in a nozzle way. Okay. So P1 is 1.8, sorry, megapascal. T1 is 400 degrees Celsius. Okay. Area 0.02 meter square. Okay. The mass flow rate is 5 kilogram per second. So M1 is 5 kilogram per second. Okay. The steam leave the nozzle at 1.4 megapascal. So P2 is 1.4 megapascal. Velocity 275 meter per second. Okay. So here there's a heat loss from the nozzle per unit mass is this much. So then there is a Q out, which is 2.8 kilojoule per kg. Okay. So the one earlier is adiabatic, because Q is 0. It basically means it will be insulated. Okay. But here, not for this nozzle. There's a heat loss, basically. Okay. So A, determine the inlet velocity. B, exit temperature of the steam. So more or less like earlier. Okay. So to find out the velocity, here we can using this equation still. Okay. The difference here is density. We cannot use P over RT because this is ideal gas. It's wrong to apply this equation here. This is steam. It's not ideal gas anymore. Okay. So then for density here, we have to use 1 over specific volume. Okay, so first we need to find out the state of the steam first. Okay, so we have this pressure, we have this temperature. So if we look at the thermodynamic table, okay, you will find out that the specific volume and specific enthalpy is this number. Okay, in fact, if you look at this pressure and temperature combination, you'll find out that the steam, I think, should be superheated. Okay, so you're probably looking at the superheated steam. So at this pressure, this temperature, this is a specific volume, this is the enthalpy. Okay, so then this will be F. In fact, I can't write S, sorry, not F. It's not G even. So this will be 1, this number. Okay? It's a superheater. So therefore, you can see this equation here. Then you'll be able to find out the velocity. Okay, I'll go through quite quickly because there are still quite a few examples that we have to go through. So I'll just roughly explain the step. Then later on, you try yourself. Okay, it's good to try as well because this can be how the test question will look like as well. Okay, so then once you find out the state 1, then we write the energy balance. We should be able to find out the second state. So T2. Okay. Then we apply the equation. Okay. So the full equation again is Q in minus Q out plus work in, work transfer out plus E in minus E out. So all this equal to 0, okay? Because change of internal energy, change of system kinetic energy, change in system potential energy, all are 0. Okay? And here, there is a Q out, there's no Q in. There's no work transfer because this is nozzle. Okay? So therefore, it get reduced to this if we express it in specific terms. Okay? So then you plug in the number. You should able to find out that the enthalpy at the outlet is how much. Okay? Here, H is not equal to CPT as well because this is again ideal gas equation. We cannot apply here. This is steam. So therefore, once we find out the H2, we have to use property table to find out at this pressure, this enthalpy magnitude, what is the temperature. You might need to interpolate between different temperature to get the correct temperature for T2. Okay, so this have to be based on the steam table. Okay, because again, here this is steam. Steam is not an ideal gas, so we can't apply ideal gas equation. Okay, just remember that very well. If it's not ideal gas, we cannot apply ideal gas equation. We must refer to the property table. Okay, so that's what nozzle and diffuser is. It changed the flow property, but there is no work transfer in the process. Okay. Then next, turbine and compressor. Okay. So unlike nozzle and diffuser, turbine and compressor is meant for work transfer. Okay. In fact, turbine is, we use it to transfer the work. Okay. Work is done by turbine. So from the flow, we transfer the work. The flow do the work, and then there is a work out for sure for turbine. Okay. For compressor, we give a work in for it to do the work to the flow. Okay. Compressor air, basically. Okay. It brings the flow to higher pressure or higher flow rate. Okay. Turbine, quite the opposite, is driven by the pressure. From the pressure, the flow develop, and therefore it delivers the work transfer. Okay. So they are opposite as well. One, you give the work to do work to the flow, and turbine, the exactly opposite. The flow do the work, transfer the work out from turbine. Okay. And how this is being drawn, in fact, is not correct. I don't agree with this. For turbine, we draw like this. This is 1, this is 2. Okay? And P1, P2, P1 always larger than P2. Okay? Mass has to be conserved. Okay? Because it's still a steady system. For compressor, sorry, here there's a work out. Okay? Whether or not there's a Q in or Q out, it depends on the turbine is a adiabatic turbine or not. There can be a heat transfer in the process. Okay. For compressor, this is turbine, this is compressor. For compressor, usually we draw this side small, this side large. Okay. You draw from the top, also no problem. Okay. But the direction is opposite. Usually the small side is the lower pressure. Here also P2 larger than P1. Sorry, opposite to the turbine. Okay. And for compressor, there's the work in. Okay. There can be a heat transfer in or out as well, depending on the compressor is adiabatic or not. Okay, but for sure, there is a work transfer in. For turbine, there's a work transfer out. Okay. Nozzle just now, there's no work transfer at all. Okay. And pump, okay, pump do what compressor do, basically. There is a work in, and P2 will be larger than P1. Okay, the difference is pump is for liquid, compressor is for gas. It's that simple. Okay, different medium, we call it differently in thermodynamics, in mechanical engineering generally. Okay, so pump is for liquid, compressor is for gas, but they do the same thing. They increase the pressure, basically. Okay, and sometimes you may also heard about fan. Okay, the same fan that you have at home. Okay, so for fan, it's almost like compressor as well. You give the work, it takes the electrical work. Okay, but the purpose of fan is not to increase the pressure that much, but it's more for moving the flow. So the pressure might not be very, very high, P2 or P1, okay, but it moves the air only. Okay, so that's the difference between pump, compressor, fan, and also turbine. Okay. Now let's look at one example then. Okay, so this is compressing air with a compressor. Okay, so air at 100 kilopascal, 280 Kelvin, okay, is compressed steadily. Okay, whenever the question says steadily, it means steady state, basically, steady flow. Okay, to this pressure, this temperature. Okay, and well, this diagram, again, the way they draw is not correct already. So let me just redraw it. It should be like this. Okay, this is going in. So P1 is 100 kilopascal. T1 is 280 Kelvin. Okay, and going out is P2, 600 kilopascal. T2, 400 Kelvin. Okay. And the heat loss is 16 kilojoule per kg. Okay. In fact, this diagram, what is wrong is just it needs to be this way around. Okay. But doesn't matter. Let's complete this. So we have Q out. Okay. So sometimes the question may ask you to draw diagram like this. So do try to draw the schematic diagram whenever you solve the problem. Okay. During the process, okay, assuming the change in kinetic energy and potential energy are negligible. Okay, so determine the necessary power input to the compressor. So how much is the work input? Okay, for this to happen. So that's what the question is asking. Okay, so then the solution is, well, again, we can start by, this is A, so therefore it's an ideal gas. Okay, so then our solution is really, again, Q in minus Q out. Sorry, plus work in minus work out plus E in minus E out. So all this equal to 0. Okay. No changes in the system internal energy, kinetic energy, and potential energy. So therefore 0. No change in the E over T. It's a steady system. Okay. And then here, there is no work out. There's a work in. Okay. There's a Q out. There's no Q in. Okay. And then we need to find out this. So then we just need to rearrange. Okay. So just rearrange the equation. Okay. And then Q out is basically the rate of heat transfer. Here, the question gives us in specific term. So therefore, we have to multiply with the mass. We'll get this Q dot out. Okay. Plus M dot, because this is this is ideal gas. So therefore, H2 we can approximate using CpT2. Okay. This we can approximate using CpT1. Okay. So then we should be able to find out work input. Okay. But if you see the solution here is still looking at property table for A. Okay. So you can do that as well. Just because it's ideal gas, there's still a thermodynamic table which you can refer to. Alternatively, you can approximate using ideal gas equation because you are treating it as ideal gas. Okay, so either way, either one should give you the correct answer. Okay, so that's how we can find out the temperature, sorry, the work input, which you solve it, you should get this number here. Okay, so that's quite straightforward example here. Okay, but this is a compressor basically. And example 7 here, this is for turbine. Okay, so also quickly, I'll just go through. Okay, so the power output of an adiabatic steam turbine. Okay, so here is an adiabatic system, which means no heat transfer, and then it's a steam. So which means in this example here, we cannot treat it as ideal gas. We must refer to property table. Okay, and the inlet and exit condition of the steam are indicated in this figure. Inlet, exit. Okay, again, here is drawn wrongly. Let me just, yes, it should be this way. Okay. And yes, I'm quite particular about this direction because this is how usually we draw turbine. Okay. And it's a adiabatic turbine, so therefore is fully insulated. So Q equal to 0. Okay? But there is a workout, which is 5 megawatts. So this number is given already. Okay. Question wants us to compare the magnitude of delta H, delta KE, and delta PE. Okay. And then determine the work done per unit mass of the steam flowing through the turbine, which means the work done per unit mass of steam through the turbine. So which means this is the E then, okay, or the delta. Okay, and then calculate the mass flow rate of the system. Okay, so then the first thing to do here, because since we have pressure, temperature, velocity, here you can see there is an altitude. Okay, so what happened is in this example, altitude is changing. So therefore, the potential energy for the flow here is not 0. Okay, so whenever there's a change in elevation in the flow, then you cannot assume this as 0. Okay, the potential energy for the system still 0 because this turbine doesn't move to a higher altitude or lower altitude, but the flow does. Okay, so because this is steam, so therefore based on this state 1 condition, we look at the saturated table, steam table. Okay, at this pressure, this temperature, you most likely find out that it's a superheated vapor. It's already beyond the saturated vapor line. So then, based on the the superheated table, you should be able to find out that H1 is this. So then you can find out H1. Okay, for H2, you notice that the questions say here there is a x equal to 0.9. This is the quality of the mixture, 0.9, which means 0.9 is a vapor, 10% is a liquid. Okay, so which means at this pressure, okay, you have to look for the state H2 based on this equation at this pressure, of course. Just like how we learned in chapter 2 before this. Okay? Then you'll be able to find out H2. So then the change in the enthalpy is basically this. That's what the question wants us to find out, the change in enthalpy. Okay, change in kinetic energy, change in potential energy. Okay, so change in kinetic energy, of course, is just the velocity difference based on the velocity difference. Change on potential energy based on the altitude difference. Okay, so this is delta H, delta kinetic energy. I'll write in small cap. This is kinetic energy for the flow, potential energy for the flow. Okay, so again, this is not always equal to 0. It depends on the question. Okay, if there is a change in altitude given by the question, then of course you have to consider that. Okay, then the rest of it, to find out the flow energy, then really we just follow pretty much the standard step just now. Write the energy equation, then you should be able to find out the work because of the flow itself. They write as W here, but really it should write in E or theta. Okay, but it's the change in the enthalpy, change in the kinetic energy, change in the potential energy of the flow. Okay, this equation here. And then the mass flow rate is the total amount of work transfer out over this one. Okay, so this is the theta or the E, the one that written earlier. Somehow this textbook, the symbol is, they mix it up, which is quite confusing. Okay, but they're using E and theta earlier, so this should be E and theta. That's what they're referring to. Okay, so the way I see, the step for the solution is more or less the same. It's just how we find out the state, the first state, property of the first state, and then how we relate to the second state only. Okay, so that's pretty much the example for nozzle, diffuser, and then compressor and turbine. Okay, so there are a few more examples at the back here, which I wouldn't go into it because they are more or less the same, like how we see earlier. So quickly, before we move into the past year question, okay, just one more time to differentiate between all these devices. Okay, so first, nozzle and diffuser. Work in, work out, for sure, 0. Okay. For turbine, there's a, for turbine, there's a work out. For compressor, there's a work in. Okay, so that's the difference between them. Okay, all of them can have heat transfer in or out. Okay, unless it's being insulated. Okay, and then all of them has mass exchange as well. So 1. Okay. Then what about throttling valve? Okay, throttling valve is pretty much like a nozzle. Okay, because throttling valve, when you close it, area becomes smaller. So mass still conserved. Okay, and then also no work transfer. But whether or not there's a heat transfer, it depends on whether there's an insulation or not. Okay, so that's throttling valve, even though it's not part of your syllabus, but just to let you know. Okay, and mixing chamber, well, you have M1 here, M2 here, and this M3 must equal to the mix of the two of them because conservation of mass. Okay, there can be Q in, there can be Q out as well. Okay, but for mixing chamber, work transfer also equal to 0 because it doesn't do work, or it doesn't require work to be done to the mixing chamber. It's just mixing two flow together. Okay, heat exchanger, well, it's a bit slightly more complicated. Okay, so M1 equal to M2. Okay, because go in here, it will flow to here. So that's steady state. Okay, but at the same time, we have two different stream. So for this, it will go around the red tube here. So M3 equal to M4. Okay, and between 3 and 4, there will be heat transfer. That's the purpose of this device. To transfer from either 1 and 2 to 3 and 4. There is a heat transfer between the two of them. Okay, there can be heat transfer between here and outside as well. Okay, unless, of course, it's being insulated. It's an adiabatic heat exchanger, then different story. Okay, and usually, not usually, pretty much all the time, heat exchanger doesn't has a work transfer as well. Okay, so really only turbine and compressor, there's a work transfer. The rest of them, there's no work transfer at all. Okay, all of them are open system, so therefore all of them have a mass exchange. Okay, so that's how we differentiate between all these devices. Okay, and the example I'll leave you to try. Okay, but lastly, okay, the last of the lecture slide really. Okay, so whenever you solve any thermodynamics problem, okay, so first of all is to define and sketch the system with energy and mass transfer across the boundary. Like all the example just now, you see the first thing I draw is the control boundary, the control volume, basically, where's the system boundary that we're analyzing. And then label, is there any work transfer, whether there's any energy transfer, whether there's any mass transfer. Okay, when you draw it out, it becomes clearer. And then whether there's a mass crossing the boundary. If yes, it's an open system. If no, it's a closed system. This is what we learned in this chapter here. This is what we learned previously in chapter 4. Okay, if it's a closed system, then mass is constant. Okay, then we just apply conservation of energy, then we can solve everything else. Okay, if it's a open system, then really the next thing we should be asking is whether this is equal to 0, the change in the mass in control volume. If yes, then it's a steady flow. Then we follow here. Conservation of mass, conservation of energy, then we find correspondingly. If it's no, then it's an unsteady flow, which there's a step to solve as well, but then it's not part of your syllabus. Okay, so rest assured that none of the question that you see will be an unsteady flow. Okay, so this is just a flow chart of how we solve a engineering problem when it comes to energy. Okay, right then. So any question up until this point? Is everything still clear? Is everything still understandable? Okay. There's a question, does that mean turbine is the only work that are not equal to 0? No, compressor as well. Compressor, there's a work input. only turbine and compressor, the work is not zero because there's a work transfer. Of course, one is positive, one is negative because one, the work go into, compressor consume work, so work going into. Okay, for turbine, it extract work, so work going out. Only turbine and compressor, the work is not zero. Okay, right. I hope everyone can still follow it. Okay, right then. So next, let's try to look at one past year question there. Okay, I think we only have another 30 minutes left. So let's quickly try to go through one past year question so that you can, I also make this your assignment too, so you can try that afterward. Okay, so for the example in the in the lecture note, please try to go through them, try to practice it yourself. Okay, then you probably will understand better from there. Okay, all the solutions are all given, so I guess it'll be quite straightforward for you to follow. Okay, so in your test two, okay, there will be two questions. This is a past year, okay, 2022, 2023. It's a 1 hour 30 minutes, not 45 minutes anymore. Okay, and two questions. First question will be on the closed system. Second question will be on open system. Okay. As for which one is a pure substance, which one is ideal gas, it depends on the question. Okay. But as you may see in the example earlier, if it's a pure substance, non-ideal gas, then we have to refer to thermodynamics table to find out the property. If it's an ideal gas, then we can still refer to the thermodynamic table, no problem. But we can approximate using the ideal gas equation. Okay. Right then, so again, I wouldn't do the calculation. I will just roughly go through the step. Then I think if all you can understand what we went through in the lecture, then I think it should be a problem for you to solve this. Okay. So here it says that 1 kg of saturated water vapor is initially stored in a piston cylinder device. So piston cylinder device is basically a closed system. Okay. The temperature is 200 degrees Celsius. Then the water vapor is cooled at constant pressure. So which means pressure is constant. Okay. To a saturated liquid. So from saturated vapor to saturated liquid. Okay. So neglect the change of the potential energy and kinetic energy during the process. First, the question wants us to show the process on the TV diagram. Okay. So TV diagram. Okay, I try my best to write the curvy V. Okay. So the water is cooled from saturated vapor, which is here, to saturated liquid at constant pressure. So this is 1, this is 2. Okay, so the process looks like this. Okay, and if you remember, for TV diagram, the constant pressure line is basically this. It didn't say how much is the pressure. but that's constant pressure line. But the state changing from 1 to 2 is basically from here, 1 to 2. Okay, so that's the answer for number 1 here. It's really quite straightforward, really. Okay. Then next, determine the boundary work for the piston. Okay, so boundary work is basically pressure multiplied with volume change. Okay, but this only gives us joule per kg, so therefore we have to multiply with the mass as well. Okay, so pressure is a constant pressure, so which means we need to find out how much is this pressure. We know this temperature, which is 200 degrees Celsius, so we can refer to the saturated table. We should able to find out this pressure. Okay, 200 degrees Celsius. If we look at the table will be provided. Okay, so 200 degrees Celsius, which is here. This is by temperature increment. So then we'll be able to know the. Wait, let me just use this instead. Okay, so we know the pressure. Okay, so it will be the saturated pressure. Okay, and volume change is basically V2 minus V1. Okay, and V2 is gas minus VF, basically. So then we'll be able to find out the boundary work. One kg. Okay, and then determine whether the process is compression or expansion. Then you just have to look at whether V2 is larger than V1. If it's larger, then it's expansion. If it's smaller, it's a compression. Okay, by the look at this, Vg I think should be larger than Vf. I think so, because gas, the V for gas should be larger. Vg larger, this is smaller. So this was V2, sorry, V1, V2. So it's a compression for sure. Okay. And then last for this part A, show the process on the pressure versus volume diagram and indicate the region that represent the boundary work. Okay, so just now was a TV diagram. So if we draw a corresponding diagram, this is V, now it's P. Okay, the dome still the same, but the constant temperature line now go like this. Sorry. Okay, so this is 0.1, this is 0.2. Okay, so this is T equal to 200 degrees Celsius. Okay. And this is only half of the answer. The question also asking, indicate the region, represent the boundary work. Okay, so boundary work is basically P multiplied with volume. So we have this pressure. So this is basically the boundary work. Okay, so it's the area under the graph. P times volume, right? This multiplied with this. That's basically the boundary work. Okay, so that's how we answer the question number 4. Okay. So that's part 1. Part A, sorry. Okay. Part B, okay. A rigid tank with a volume this much, okay, initially contained a mixture of liquid water and vapor at 100 degrees Celsius with quality of 0.2, which means the overall volume is 0.1 meter cube, but 20% of it is liquid. Sorry, no. 20% is vapor. Okay. The mixture is then heated to a temperature of 150 degrees Celsius. So initially, 100 degrees Celsius. And then we heat up, which means Q in. So then it becomes 150 degrees Celsius. Okay. So assume the tank to be stationary, which means kinetic energy 0. The tank is not moving anyway, no altitude change. So this is 0 as well. Okay. So then the question wants us to determine the final quality of the mixture in the tank. Okay. So in order to solve this question here, okay, first of all, from here, we can find out the specific volume first, okay, because it's a mix of vapor and liquid, okay. So this we can calculate based on F plus X Fg. Okay, so then we know the specific volume in state number 1, this state number 2. Okay, the reason being is because it's a constant volume. It's a constant volume. It's a solid tank. So therefore, V1 equal to V2, specific volume. Okay, so once we calculate this, we know this. Okay, then it's a matter of at 150 degrees Celsius, how much is this? Okay, if this is larger than V2, then we're talking about mixture, right? Because on the TS diagram, this is Vg, okay? If our V2 is smaller, which means a mixture. If it's larger, which means it's a saturated vapor. And in this case, I think if you find the answer, you should get that V2 is smaller. So therefore it's a mixture. Okay. And then from there, you can find this, you can find this, and then you'll be able to find out X2. Okay. So then you know the quality of the mixture. Okay. Because in fact, the question asks you to find out the final quality. So it is, in fact, I think you solved it correctly, then it should be a mixture. Okay. And then the total mass of the tank of water. Okay. So we have this. So V is basically equal to mass multiplied with V1. So then we should be able to find out the mass. Okay. And then write the energy balance of the equation. Okay. So the energy balance of the equation, Q in minus Q out plus work in minus work out, E in minus E out, that will be equal to delta U plus kinetic energy plus potential energy. Okay, we always write the full equation first. Okay. So this will be 0. No mass exchange because this is closed system. Okay. No Q out. There is Q in. No work out. Okay. There's no work out because, first of all, there's no work going out. There's no boundary work as well. If there's boundary work considered as one workout. Okay. So then you get your equation. This equal to this. Okay. And delta U basically equal to M multiplied with delta. Well, the change in internal energy between 1 and 2. Okay. And then here, determine the boundary work. Okay, because the boundary is fixed, so therefore boundary work is basically equal to 0. Okay. Sometimes the question is a mix between theoretical knowledge and calculation. Not everything needs to be calculated. Okay, because constant volume. So therefore, boundary work here is basically 0. The question is just testing your understanding. Okay. And then determine the amount of heat transfer in the process. Amount of heat transfer, which is this one. Okay. So here, you know M. We know M. Yes, we know. Okay. M we already find out here. U2, we can find out. It's not a problem. Once we have this, U2 is basically U fluid plus X2 UFG. U1 is also UF1, of course, plus X1 UFG1. This is 2, of course. Okay. So then you should be able to find out the amount of heat transfer here as well. Okay. And then show the process on TV and PV diagram with the respective saturated line. TV diagram. Okay. So what happened is the volume is constant. Specific volume is the same. Okay. So this is number 2. Number 1 is really from here. Okay, because volume is constant. So it was changing from this state where the temperature is 100 degrees Celsius to 150 degrees Celsius. Okay, so obviously in this case, pressure is not constant. P1, P2. Okay, but the phase, the state is really from 1 to 2. So it is purple line. Okay. If we are talking about the PV diagram, okay, constant temperature line, 150, 100, okay, is still changing from here, sorry, from here to here. Okay, because here V1 equal to V2. Okay, so really both are straight line going up. Okay, because it's a constant volume from, it's a rigid tank. So what we're dealing here is constant volume problem, and here is a moving boundary problem. Okay. So far, okay? With this past year question. Yeah. Okay. So I think the question is more or less similar with the example as well. Okay. So give it a try. Okay. When later on after this, before Tuesday, obviously. Okay. So next, let's quickly, well, it's already 11, so I'm going to take a bit more time just to finish going through the question number 2 here. Okay. So question number 2 will be on the open system. Okay. So here the question is slightly different. Part A, B are more on theoretical, and then C is a calculation. Okay. So let's go one by one. Okay. Consider an open system with one inlet and one outlet. Okay. State that the mass content of the system, whether it's increase, decrease, or constant for the following case. So which means we have a okay. We have a mass in, we have a mass out. Okay. And the question wants us to determine the dm control volume over dt, whether it's increase, decrease, or constant. Okay. So incoming mass flow is higher than outgoing. So that obviously is increase. Incoming mass flow is lower than outgoing. That obviously is decrease. If they're the same, that obviously will be the same, constant. Okay. So it's really just testing your understanding with mass balance on here. Okay. Second, Sorry, part B, is it possible for steady flow system involve boundary work? Okay, and the answer for that is not possible because for the steady flow system, okay, it basically means that volume cannot change as well. Okay, volume is constant as well. Because if volume is not changing, boundary work is basically pressure multiplied with volume. Okay, multiply with the mass, of course. Sorry, not m dot. Okay, but if volume is constant, which means there cannot be a boundary work. Boundary is not moving, it's not doing work at all. Okay, so that's the answer for part B. If the boundary is moving, then yes, there can be a boundary work. Okay. And then last part here, okay. So this here is a compressor. Compressor therefore operate A. When it's operating A, which means this question is ideal gas from. Okay. It's a compressor, which means there's a work exchange. There's work into the compressor. Okay. So it's used to compress air from 100 kilopascal, 25 degrees Celsius, to 2 megapascal, 420 degrees Celsius. Okay. The air enter the compressor at the velocity of this, okay, through the inlet area of this, okay, and exit through an area of this area. Okay. Heat loss this much occur during the compression process. So which means it's not a adiabatic compression process. There's a heat loss. Okay. So the change in potential energy is negated. There's no change in potential energy. So the airflow itself, there's no altitude change. Okay. And the air is treated as ideal gas. Very nice of the question to inform this as well, but then you should really know already because it's air. Okay, with gas constant of this and Cp value of this. So you can use this to approximate the enthalpy, for instance. Okay, and density as well. Okay, so then the question wants us to sketch the schematic diagram of the compressor and label it completely. Okay, so it's a compressor. So we draw the compressor that looks like this. Flow go in here, out from here. This is state number 1, state number 2. Okay, so inlet pressure 100 kilopascal. Okay, and velocity. Oh, sorry. It's a very bad habit to write it in a small v. It should be the straight sheriff v. 25 per second. Area 0.17. Okay, so this is the inlet state. Okay, the outlet state P2 2.0 megapascal, T2 420 degrees Celsius. A2 is 0.09 meter square. Okay, and there's a heat loss, don't forget. So Q out, because it's per kg, so therefore I write it in a small q, 18 kilojoule per kg. Okay, and this is compressor, so therefore there must be a work in. There must have. Okay, and our control boundary is basically here, the A. So there's a mass exchange, there's a heat exchange, there's a work exchange as well. Okay, so that's the answer for part 1 here. Okay, so always draw the schematic diagram, label everything, so then it's very clear. Otherwise, it's just a long paragraph, right? So draw it out. It's much easier to visualize it. Okay, and then the question wants us to determine the mass flow rate of the air. Okay, and seeing from here, inlet condition, state 1 definitely more complete. So therefore, we can calculate the mass flow rate based on here, rho A V, V in the velocity. Okay. Density, P over RT, because this is ideal gas. A1, we have it. V1, we have it as well. So then we should be able to calculate the mass flow rate, no problem. Okay. And then the outlet velocity. Okay, so for the outlet velocity, well, of course, this M1 equal to M2, conservation of mass. Okay, so M2 will be rho 2, A2, B2. We have pressure, we have temperature, so which means P2 over RT2. A2, we also have it. So we should able to find out B2. This is a known value, okay? Because we have pressure, we have temperature, so we know the density of the outlet. So this shouldn't be a problem at all. Okay. Then the power input to the compressor. Okay, so for this, of course, we have to write the energy balance. Okay, so Q1, sorry, not plus, minus QR. Okay. This equal to 0 because there's no change in the internal energy, kinetic energy of the system, potential energy of the system, right? So equal to 0. And then from here, let's cross out what doesn't applicable. There's a Q out, there's no Q in. There is a work in, there's no work out. Okay, so then let's rearrange it slightly. So then for us to find Q in is basically Q out plus E out minus E in then. Okay. And Q out is basically M dot Q out. Okay. M dot Q out. So this one, no problem. Plus M dot H. I'll write it as theta first. Yeah? Okay. By the way, the in is 1. This is 2. but we know that they are the same. So therefore, we can just write it as 1m. Okay. And this here is really H1, sorry, this is out, so 2, H2 plus V square over 2 plus GZ2. Okay, so here H1 plus V1 square plus GZ1. Okay, so then from there you should be able to find out work in. Okay. The question wants us to ignore the potential energy. So therefore here, even though I write the full equation, this should be 0. Okay. H, we can use Cp T1, Cp T2. Velocity, we have it. So shouldn't be a problem for us to find this. Okay. So just like that, we should be able to find out this. Okay. And the last one, explain without calculation what will happen if to the power input of the compressor if the outlet air temperature, which means T2, is reduced by cooling. If T2 drop, then what will happen? Okay, use the energy balance equation to support, which means this equation. Okay, what will happen if T2 decrease? What will happen to the work input? Okay, so for this, I'll let you to find out. Okay, once you're able to write this equation out, I think shouldn't be a problem for you to answer this question. Okay, right, so that's one example of a past year question, how the question may look like. Okay, and compared to your test one, I think this definitely involve much more calculation. Okay, so I think it's definitely a good idea that you try the example in the lecture note again. Okay, and practice. I think that's the only advice I can give. Once you practice a few example, you might find that the steps are more or less the same sometimes, because the question doesn't change so much, to be honest, for thermodynamics problem. Okay, right. I think that's probably enough as well for today. And I hope everyone still can follow. Okay, even though the calculation might be pretty long. Okay, so give it a try. Okay, try the example in the lecture note, and this I also make it into the assignment already, so you can find it in the e-learning. So please get it from there, and after you've completed, please upload it back to the e-learning, submit it there. Okay, don't submit to the share folder anymore. Okay, right. So that's all for today. I think that's definitely enough. There's a lot we have covered today. So thanks again for making a time tonight for the class. So good luck with your test too. Okay, so I think you still have a few more days to go through the material and try the example, everything. Okay. So any things anyone want to ask before we end the class? Okay. Right. If no, then thanks very much again, everyone. So have a good night then.
Right, sir. Thank you, sir.
Yeah, thank you.
Thank you, Doctor.
Doctor.
Yes.
Can you upload the recording for today, just for us to refer back?
Recording. I didn't record that.
Oh, it's okay, it's okay.
Yeah.
Thank you,
But
Doctor.
the notes, the lecture that I draw, I can upload that into e-learning as well.
Okay, sure. Thank you, Doctor.
Okay.